Okay, what's going on this section 2.3 is graphing polynomials pretty much. One of my favorite units, mostly because it kind of pulls a lot of things together that we've been working on in Algebra 2, pulls in what we did last unit. Some vocabulary piece that's going on here is you have two things. When you have a polynomial, first off, this written in this nice long chain of things, but this is in standard form mostly because you're starting with, you have a leading coefficient, you have an x that has a power, and it's in descending order. The leading term, which would be this one right here, that's your leading term, and its power designates the degree in which the polynomial is. So if it's the n is actually 3, it's to the third degree. If x is the 5, it's the fifth degree. I'm trying to think what other things you need to know. A to the n, this one right here, this is your leading coefficient. That pretty much kind of tells you someplace what's going on, how it's going to graph. What other things do you need to know? This number at the end, that's your constant. I can write nicely here. That's your constant. It's not multiplied by an x with a power. So what they want us to do, we're going to, like I said, pulling some stuff in here on regards to graphing. In the first example that they give us is, sorry about that, the first example they're giving us, they want us to graph the transformations of these monomial functions. I need to probably remind you what a monomial function is. A function that only has one term. So what they've asked us, it's not written here, but they're asking you to graph g of x if f of x was 4x cubed. Well, that 4x cubed is a monomial, and we know that it has a vertical stretch from the parent function, the parent cubic function, vertical stretch of 4. So, but the parent one would go through the origin. It would kind of look like, if I was to sketch that over here, that would look something like this. Kind of goes to the origin. Not a really good picture, but it's one of those things that the monomial is going to go through the origin. It doesn't have a shift left or right yet. That's what the parent, that's what 4x cubed is supposed to look like. What it wants us to do is graph that one, so we know from the f of x, if that's the monomial, it's going to have a horizontal shift of 1. Well, that's all well and good. I know that it's going to cross the x-axis. This is kind of going to be kind of hard. I don't know if I can zoom in, but it's going to cross the x-axis at -1. Well, that's great, but now let's see if we can't find out where it's going to cross the y-axis. One of the things I want to remind you about is how to find the y-intercept. So if I want to find the y-intercept, I'm going to erase this. This is not graphing that. If I want to find the y-intercept of this function, at the y-intercept my x is equal to 0. So when x is equal to 0, if I plug that into this function, if I evaluate g at 0, we should get 4 times 0 plus 1 cubed. Well, 0 plus 1 is 1, 1 cubed is 1, 1 times 4 is 4. So where it crosses the y-axis is up at 4. 1, 2, 3, 4. I'm not sure if I can actually do that with my thick pen. 1, 2, 3, 4. Nope. Anyway, so it's going to look something not really good with this really small graph paper and really thick pen. Let me see if I can do it with my finger. 1, 2, 3, 4. Yep. Better luck with my finger. Crosses the x-axis at -1. That's good. Alright, so it's going to have looks. I can't do this with this pen. Sorry, guys. It's going to cross right here. Right, what that probably should look like is this. There we go. Okay, so that's g of x. All right, let's do the same thing with h of x. And it's asking us to transform to graph it from its monomial. And I imagine the monomial that it transforms, it doesn't have it here, but the one that it transforms is this. And let's just say, let's do this in blue. The f of x was supposed to be a monomial, but it doesn't say that in there. It's supposed to be negative x to the fourth. Okay. Now, a negative x to the fourth is a monomial. It's supposed to open down. Since it's to the fourth degree, that needs to, my two ends are going to go down, down. I'm going to explain that in just a minute. I'm going to go over this leading term test for polynomial end behavior, but I kind of want to just approach this one as a transformation or translation of the monomial. Well, we know it's going down, so my end behavior is just going down, and if the parent function probably should look like, it just kind of goes this, and it sits at that when x is equal to 0, kind of like that. Well, it wants us just to transform that, so if I do it a different color, I know I'm going to go move to the left, or the right 2 and then up 5. Well, let's do that in red. So I'm going to take that, go to the right 2 and up 5. 1, 2, 3, 4, 5. And it's going to sit there a little bit. And it crosses at 3.5. With this, it's not going to do us any justice because this it's supposed to look like this. Okay, now let's talk about end behavior polynomials and characteristics of what they're supposed to look like. And end behavior and how they behave, like what that is pretty much what it means is what it says, is what's the graph doing at the ends of the graph. As in other words, when we allow x to go either positive, get more and more positive, or more and more negative, what's the end of your graph doing? What are your y's doing? Up here in this table, I'm going to slide it over here a little bit better and kind of talk about that for just a minute, mostly because I did a little review on end behaviors, but what happens is when your degree of the polynomial, if it is an odd function, it's going to kind of mimic that of their end behavior is going to mimic that of a line. If your a is positive, and your degrees, like if it's negative, it's not negative, I'm sorry, if it's an odd number, 1, or actually it's supposed to be more than 1, if it's 3, 5, 7, 9, if your degree is odd, its end behaviors are going to look that of a line. And let's look at this right here. If I'm looking at this first graph, I kind of went over this, like you can go back and watch the end behavior, but it's the end behaviors of this. If your a is positive, that means the ends of my graph is going to pretty much mimic that of a line. Like if I had a positive sloped line, my end behaviors of that line are pretty much that, like a line. So as x's get positive, my y's get positive. When my x's are getting smaller and smaller and smaller, my y's are going smaller and smaller and smaller. Okay, if you have an odd degree polynomial and your a is negative, it's going to mimic that of a line with a negative slope. And what that means is, as x's get smaller, when they go this way, my y values are getting bigger. And as x approaches positive infinity, my y's are getting smaller. So that mimics that of a line. If you have an even powered polynomial, if it's 2, 4, 6, 8, well actually it's more than 2's are quadratics, but if you have something that's 4, 6, 8, those end behaviors are going to mimic that of a quadratic, what we learned in Algebra 2. If you have a positive a, if your a is positive, it means your graph is supposed to open up. That means it looks kind of like that. So as x's get negative, my y's go positive. As my x's go positive, or they get bigger, my y's go positive. So that means it's up, up. I have two positive, and f of x is approaching positive infinity. If a is negative, and it's might have an even polynomial, so that means it's going to open down like that of a quadratic that's opening down. My end behaviors are going to go down, down. What that means is as limits as my x's get negative, my y's are going down. As my x's get more and more positive, my y's are still going down. even polynomials, the end behaviors are going to go in the same direction. Okay, so they're going to either go down, down, or up, up. If your polynomial is odd, your end behaviors are going to go in opposite directions. So if it helps, odd end behaviors go in opposite direction. Okay, and they'll start with an O. If your A is positive, it's going to look like that of a positive. Your end behavior is going to mimic that of a positive slope line. If your A is negative, your end behaviors are going to kind of look like that of a negative slope line. All right, with that being said, let's go and talk about this. And we should probably be able to do this without even, you're going to be expected to know how to do this without the aid of a calculator by reading what's in the function. You're in pre-calculus now. There's a lot of stuff involved in this function. You can pretty much pick it apart and tell you what's going on with it. Well, the first one, they give you f of x is 2x cubed. It is an odd polynomial. My a value is 2, so and since it's positive, the end behavior is gonna mimic that of a positive slope line. So when my x's get negative, then when I'm going toward negative infinity, my y values are going down. They're going toward negative infinity. As x's approach positive infinity, my y's are going to positive infinity. They go in opposite directions. Now what this is asking for b is you don't have to graph it. They want you to figure out what the end behaviors are doing just from the equation. Well, a in this problem is negative 3. My a is negative. It's less. A is less than 0. That means that I'm an important thing, and my degree is 4, so it's an even polynomial. That means my end behaviors are going to have to go together. They're going to go up, up, or down, down. Because my a is negative, that means my end behaviors is going to mimic that of a quadratic, and it's going to go down, down. So we can fill in this blank. As x's get positive, my y's are getting more negative. As x's get more negative, my y's are getting more negative. They're going down, down. All right, with that being said, let's see if I can flip the paper over. Okay, I seem to have deleted this previous one, but they're asking us to describe this polynomial. I'm going to describe what I can without the calculator. I'm going to put it in the calculator. I'm going to graph it, kind of edit a slide onto the next of it. But the degree of this one, because this is my it's the highest exponent or highest power, so my degree is the third degree. Because it's odd and my a value is positive, is 1 right here. Go ahead and erase that. My a is positive. That means my end behaviors are going to go in opposite direction. It's going to mimic that of the line. So my end behaviors is limit as x approaches positive infinity. F of x is going up. And his limit as x goes to negative infinity. F of x. Limit as x goes to negative infinity, f of x goes down. Okay. Now my viewing window in the calculator is, if I do it from negative 5 to 5, and then from negative 25 to 25. Alright, again, be reminded that this is my x values, x min and x max, and these are my y min, y max. Alright, I'm going to stop right there, and then the next slide, I kind of draw the picture and I do the extremas. If you can put this in your calculator, you'll be able to see what it looks like in your calculator. Graph this, what it kind of looks like. If this is your graph, and this mimicking what it should look on the calculator, it does this. It kind of does this, crosses. So I have a 0 here, 0 here, 0, 0. Roots and solutions all mean the same thing. But why I wanted to do this, so I have crosses the x-axis is at negative 3, I'm sorry, negative 4, negative 1, and 3. But one of the things here I want to point out is where this graph is positive and where it's negative seems to be an issue. From right here, from this point, from that 0 to this 0, the graph's positive, and this one's positive here. So if I want to write f of x is positive, and to remind you, if this is at negative 4, it's positive between negative 4 and negative 1, a break, and at 3 to infinity. Alright, well, let's do when f of x is negative. F of x is negative from here down, and from those 2 points. Alright, well, it's negative from negative infinity to that 0, which is at negative 4. I'm going to print parentheses around that, guys. I'm not including negative 4 because at that particular point it is neither positive nor negative. It's actually 0. So, alright, then there's a break, and then it starts from negative 1 to 3. Alright, just wanted to kind of recap that. Again, this graph did cross 3 times. The end behaviors go in the opposite direction. Odd behaviors have to cross the x-axis at least once. So we're going to have at least 1 0. Sometimes there's multiple zeros on that one. Alright, let's see if I can't go back. Alright, let me see if I can add a file where I was. 2, 3. Oh, that's not what I wanted. Alright, I am here. This one. Alright, this in letter B, this time it's to the 4th degree. Let's see if I can't. Alright, so the 4th degree, and the reason it's to the 4th degree is because my highest power is 4. The leading coefficient is 2, because 2 is greater than 0. It's positive, so a is greater than 0. And because my degree is even, that means my end behaviors are going to, again, they're stick together. They're either going to go up, up, or down, down. Because a is positive, that means my end behavior is going to mimic that of a quadratic. It goes up, up. So my end behaviors limit as x approaches negative infinity. F of x equals positive infinity. They go up, up. The limit as x goes to positive infinity. My y's still go up because they both go up, go to positive infinity. Okay. My viewing window on this one is negative 5. 5, those are my x max, min and x max. And then my y min needs to be negative 50. And my y max needs to be 50. Okay. I'm going to stop there because I go into the whole local extremities and positive and negatives on that one. So, this, my graph is going to look like this. Some curves and it crosses, comes down, dips, does that. Okay, so it crosses 1, 2, 3, 4. So this one is not very deceiving. It actually does cross 4 times. That's the power. The highest exponent pretty much tells you how many times it should. Now, even functions don't have to cross. They can be, all the roots could be imaginary. But this one does have 4 of them. It looks like I have x values at 1, 2, 3, at negative 3. Actually, it's at negative 3.02. I have an x value at negative 1.97. 967, sorry. And at 0.97. God, I like these 0.97s. 179. And at so across there's supposed to be 4 zeros. And at 3.008. Alright, so those are my zeros. I have a couple of, I have two maxes. No, I'm sorry, one local max. Local max is at, I'm trying to look at this, it's at negative 3.98 and 30.6. I don't know if it's 38. And then that's my local max right here. And then I have two local mins. One of them is at negative 2.556. And the other one is at 2.205 and at negative 42.934. Okie dokie. So that's what's going on that function. I'm trying to think. The end behaviors are going up as x approaches. Let's do that in proper notation. So limit. Alright, Miss Andrews, the limit, it's the limit as x goes to negative infinity, f of x approaches positive infinity, as the limit approaches positive infinity, f of x equals positive infinity. They're both going up. Okay. Okay, where we are is we're asking to write functions when you have multiplicity of functions. Now what they've given us is they've given us some zeros or roots, and they've given us listed like this, but what typically we want to write them as is this: x equals negative 2, x equals negative 4, x equals 7. These are as roots. Now, in pre-calculus, how you're going to see this, I'm just going to put this over here. This is more of what you're going to see it as. F at negative 2 equals 0, f at negative 4, 0, f at 7, 0. Okay, so what that means is this is where the graph's going to cross the x-axis. And so let's write it. This is in root form. Let's write it in factored form. Of course, in factored form, we go like this. I'm going to do this. These are roots. In factored form, it's going to be x plus 2, x plus 4, and x minus 7. Guys, we spent a significant time on algebra 2. Given in roots, write them as factors. Given in factors, write in as roots or solutions. Okay, how they want this polynomial actually written is x plus 2, x plus 4, and x minus 7. Okay, now we'll leave it like that, assuming that until they give us another point, we can't solve for the leading coefficient. We're just going to assume it's 1 right now. We're also going to assume that it's positive, unless told otherwise. And we can find it, the leading coefficient another way by plugging values for x and y, or finding something that we're going to assume that a is positive and a is 1 greater than 0. Okay, so I'm going to graph this, what it looks like. Hopefully it should zoom in. I don't know why it's not zooming in. There it goes. Okay. So I'm going to have at negative 2, at negative 4, and at 7. 1, 2, 3, 4, 5, 6, 7. Okay, because a was greater than 0, it was positive. And also, the degree of this polynomial was 3, because it had 3 roots. If I added up all the powers of my factors, it would be 3. Alright, because it's odd, that means my end behaviors are going to go in opposite directions, and it's positive, so it's going to mimic that of a positive slope line. So that means that my end behaviors are going to look something like that. Then we're pretty much going to fill in the blanks. I'm going to come up here to this root, cross it, because my factor just has the first power, go up somehow, so a certain amount, I don't know how much. Then I'm going to come back down and cross at -2, go down, and then be able to cross back up at 7. And then my end behavior is going to be that of going positive infinity. Alright, that's what that's going to look like. Let's see if I can... Alright, so we just graphed that one. Let's do the same thing with choice B, or example B. Alright, so they give us roots. I'm going to write them in this form. Alright, so what's weird is that I have 3 repeats itself 3 times. So there's 1, 2, 3 times. So that's a multiplicity. If it repeats itself at that root more than once, it's a multiplicity. What happens there, and when it crosses the x-axis, it's going to sit in, like, because it's happening 3 times, it's different things happen. So I'm going to write this in factored form. So what happens, see, f of x is x minus 3, x plus 2, and x plus 7. Okay, now because there's 3 of these, I have 3 roots at 3, I'm going to put a power of 3. It happens there 3 times. Because this happens at -2 twice, I'm going to put a 2 here. Okay, and then this happens over here it's the root at -7 only happens 1 time. I can write a 1, or you can leave it as 1. Now, if I add up all these powers, there's going to tell you the degree of the polynomial, 3 plus 2, or I can count them, 1, 2, 3, 4, 5, 6. It happens, there's 6 things. Because there's some multiplicity, I'm going to write it in factored form just like I did it here. But my degree is 6 because I add up all those powers. Because my degree is even, and again my leading, I don't know what my leading coefficient is until they told us, so I'd give us a point that I can solve for A, that it's going to be positive. Because I have an even degree and my A is positive, that means my end behaviors are going to go up, up. Even degrees, their ends stay together. So I'm going to graph this one. So at -7, 1, 2, 3, 4, 5, 6, 7, I have a root at, I gotta look it up, hold on a second. I have a root at -2, then I have a root at, not -7, yeah, -7, -2, and a 3. 1, 2, 3. So it's crossing, something's happening in all these different places. The end behaviors are up, up. And because I have a multiplicity, this one right here, when x is 7, at 7, my power degree was 1. When I was at -2, the power on that one was 2. So that's gonna, like, what's gonna happen there is because it's even, it's gonna like tangent. My y values are just gonna not change the sign. And then the other one, this was 3, it's actually gonna cross. It's just gonna sit, and it's gonna take a minute to cross it. Alright. So, I did this wrong. I did this backwards, guys. This is happening at -7. It's a cross. It happens only power 1, hence the power up here. It's a tangent at 2, just because it repeats itself twice. And then it sits And this one at negative 3, its degree is 3. So it's going to kind of sit. So what I'm going to do is fill in my blanks here. I'm going to come from my end behavior. I'm going to come down here. It's going to cross at 7 because my power is 1. I'm going to go down, and I don't know how far it's going to go down. Then it's going to come back up here and touch, just touch there at negative 2. It doesn't cross because it's like at power of 2, my y values don't change their sign. So it's going to hit that x-axis, touch it, and turn back around. It's like a hockey puck. It touches it and it kind of ricochets back. And then my y value is going to go down, come back up, and cross. Actually, to be honest with you, it does more. It has to sit there. Because the power is 3, it kind of comes up at, at 3. It's eventually going to cross, but it kind of sits and hangs there for a minute. Some people call it a kiss, some people call, I don't know, I called it a wiggle when I learned it, so hence that's what that one's going to look like. Alrighty. Alright, so we learned if we're given zeros, how to graph it, and what happens if they have multiple, something's going on at the root, if there's a multiplicity there, what it's going to look like. Now if we're given it in standard form, we need to be able to factor and define what's going on there. Alright, so I'm asked to find the zeros of polynomials by factoring, because we've done lots of factoring in Algebra 2. First thing you need to do, factor out the GCF, which happens to be x. So, factor in x. So, x goes into x cubed, x squared times, minus what's left over here. X goes into x squared, x times minus 6. So after I factor out GCF, I got that. Then I need to factor what's left inside my parentheses. And that's going to be factors of negative 6 add to negative 1, which are negative 3 and 2. Okay, so these are, it's in factored form. Again, this is the reverse of, these are factors. It's reverse of what we were just doing a minute ago. And then my roots are zeros. I set each factor to 0 and solve for x. So apparently, again, these are my roots and zeros. Crosses at 0, 3, and 2. These are where crosses x-axis. It apparently crosses 3 times. Nothing really deceiving there. My degree was 3. It tells me I'm supposed to cross at least, or it could cross 3 times. It has to cross at least once because it's an odd degree. I don't have any imaginary roots. Alright, now let's talk about b, though. That's where it's kind of different. b, I'm going to factor this, and there's a difference of 2 perfect squares. So I'm going to take the square root of the first term, which is square root of x to the 4th is x squared, minus the square root of second, which is 9. And then other root factor is going to be x squared plus 9. Difference of 2 perfect squares, guys. This is one of those patterns we did in Algebra 2. Alright, but now I still, see in there, I still have a difference of 2 perfect squares, so I can keep factoring. I'm going to factor this second root, and the first one, again. But I can't factor this. I can't factor x squared plus 9. This is where I was talking about. I have some imaginary roots in there. So this is in factored form. It's going to cross at 3 and at negative 3. Those are my real roots, and the other two are imaginary. Can't see them on a Cartesian plane, what they look like. They're hidden and there's some kind of jump. But if I kind of want to guess what it looks like, something like this. Crosses at negative 3 and at 3. I'm going to have my leading coefficients positive, so my end behaviors are going to go up, up. Crosses here, here. It's going to go down here, and something weird happens down there. Crosses and go back up. So it's going to look something to that effect. Alright, there you have it.